Hi, kids. Okay. We're going to do a sample problem here. Object weighs blank newtons outside water and blank newtons underwater. Determine the buoyant force within the object's found. If you guys have never seen this before, that hopefully you guys should have experienced where, like if you try to pick a rock up outside, it's really heavy, but in the water, it's not as bad, because you can lift it up in the water, but you can't lift it up outside, because of this idea of buoyant force. So I have my random object. Here's a random cube of something, okay, if I had my random cube of something, it is going to weigh, okay, if you can see the number there, we see it's roughly 0.92 newtons outside, and then inside, oh, if you can't tell, there's some water. See the water, everybody? Water. Inside, under the water, it looks like I got about 0.5, I don't know, it's a little over 0.58, so I'll say 0.59 newtons, okay? So, 0.92 newtons outside, 0.5. So, well, guess where we're going to start? Did you guess it? Did you guess it? Well, that would be a free body diagram. So there is my little object. It looks just like it. And then, force of gravity. This is when it's under the water, by the way, so if you want, there's my water. Force from the scale, and then I'm also going to have this buoyant force going on. Okay? So that is, and if I do my second step, is going to be Fg minus Fs minus Fb equals 0. Then if I plug my numbers in, Fg is 0.92 minus the force of the scale. When I'm under the water, it's 0.59 minus Fb equals this, which should make sense because my buoyant force is going to be the difference between those two. So if you do some math, 0.92 divided by 0.959, oops, not divided, you rotten man. All right. So I get my buoyant force to be 0.33 newtons, okay? Hopefully that makes sense. So that's the buoyant force. That means, what that means, and this is what Archimedes' principle says, is that what that is saying is the weight of the water that this little cube displaces is going to be 0.33 newtons, okay? So if I wanted to figure out the volume of that, the volume of this thing, because whatever the volume of this thing equals the volume that it displaces, then if I do I guess I'll do it over here, the buoyant force equals rho Vg. I personally like to write it like this because, just remember, okay, rho times V is mass. So really what we're saying here is the mass of the water displaced times gravity. Oh, that's the weight of the water. Hooray. So if I plug my numbers in, 0.33 equals, for water it's 1,000. My volume, which I'm looking for, times 9.8. So if I do my math, 0.33 divided by 9,800, and you get a really small number. My volume is 3.37 times 10 to the minus 5th meters cubed. So a really small number. So let's see how accurate it actually came out to be. So if I was to use my meter stick and measure the length of the side here, okay, if I hold this up so you can actually see, hopefully you can see it's about 3.2 centimeters. Everybody see? 3.2 centimeters. So if 3.2 centimeters is 0.032 cubed equals, so 0.032 cubed equals, oh, not bad, 3.28 times 10 to the minus 5th meters cubed. So if I was to do my, percent air there, so the difference between them, minus 37 e to the minus 5th, divided by the actual 3.2738 e to the minus 5th, times 100, I get 2.8% air. Not bad. Hey, not bad. I like when physics works. So yeah. All right. Bye.